Greetings, let's prove a statement in graph theory that is as follows. So let's say G has a cycle if and only if G isn't minimally connected. So what this says is basically two implications, an implication from here to here and from here to here. That's the function of having an equivalence logical statement. That means that this statement can be true if and only if this statement is also true. So these two statements are equivalent logically. And so if we want to prove this, we can take the implication from this statement to this statement, and this statement implies this. If we prove that, and if we also prove that this statement implies this one, which would be the other side, other direction of the implication, then we have taken care of the thing. So let's see. So if G has a cycle, then we want to see that that implies that it isn't minimally connected. So a graph is minimally connected if, whenever you remove an edge, it's disconnected into components. But removing if you remove an edge, this means that I remove some edge E from the graph G. If that edge is on a cycle inside that graph, the graph is still connected. But a minimally connected graph will no longer be connected if you remove any edge. So it must be that if G has a cycle, whatever edge you remove from that cycle, the remaining graph will still be a connected one. That's the function of cycles. I can show an example of it. So let's say you have this. If I remove, for example, this edge, here it was a graph of a cycle. But if I remove an edge from the cycle, we see it's still connected. All the vertices can have path from each other to one another. So between one another. And so we have this implication direction. Okay? And for the other side, well, we can say that there exists some edge on the graph, and the edge will be between two vertices A and B, such that G minus E, and this is for the other side of the implication. So now we are trying to prove that if G isn't minimally connected, then it has a cycle. So if we remove that edge, if we have some graph that is not minimally connected, that means there are some redundant edges, such that we can still have paths between any vertices, even if we remove that particular redundant edge. So imagine that this edge is that redundant one, and so if we remove it, that graph is still connected. So here we see that if that happens, the graph can be imagined like something like this. We have that one redundant edge, or there can be more redundant edges, but for an abstract idea, that one redundant edge, and we say that even if it's removed, there still is a path between these two, because that's the idea of connected graphs. They are not minimally connected. So if it isn't minimally connected, that must be that between some edge AB, there is more possible ways we can have a path between the two vertices. So between some vertices A and B, there must be more ways. Namely, there must be that edge between them that will break this connection, but then if it's not minimally connected, then in that scenario that causes the graph not to be minimally connected, there can be more things that cause the more edges that are so somehow redundant that cause it to be not minimally connected. But let's say this edge is an abstract example inside that. So if we remove that edge, if it wasn't minimally connected, we still have an alternative route. So there exists still a path between A and B. And so that implies that G has a cycle, because you see this thing is a cycle. Okay, if I draw it like this, there must be some path. So some vertices on the way are connected by edges from A and B. And also there was this edge E between A and B. So all this together is a cycle, because it's a closed path like this. And so we also prove from the right to the left side that if G isn't minimally connected, then it has a cycle.